Okay, so for 5.2, we're going to take a look at the natural log function and specifically what things that we would integrate to end up getting a natural log function. So, first essential question has you looking at all these different integrals, because sometimes as we're getting ready to review and test and things like that, we don't remember exactly what forms are going to turn out to go into natural log when I integrate, and then which forms I just use old rules for. So that's why that's an essential question. And then today we're going to take a look at integrating things that are of the form 1 over something. And so that's, oops, sorry. That's where I've got just this open box. You're going to integrate something 1 over something. When we are looking at that, what are some other good U substitution choices? And then there are going to be some times today where it's going to help you if you would first do some algebra, either do synthetic division or do long division to rewrite what you have before you actually then start trying to integrate. So it's your job today to integrate things of the form either 1 over x or with u sub as it gets more complicated, 1 over u. The reason why is because we looked in 5.1 at how you differentiate natural log of absolute value of x. And so the derivative goes this way. And we've learned in 5.1 that the derivative of natural log of absolute value of x is 1 over x. So that means if we want to reverse and we then want to integrate 1 over x dx with respect to x, then we're going to get natural log of absolute value of x plus c. So we already did the forward direction yesterday, and we ended up differentiating natural logs and getting things of the form 1 over something. So now if you're trying to integrate something of the form 1 over something, you're going to go backwards and end up with a natural log. Okay. The reason that those absolute values are there and they're so important is because if you remember from the graph of y equals ln of x from yesterday and from your algebra classes, you've got a vertical asymptote at x equals 0. It goes through the coordinate 1, 0. It curves up like this. You can't take the natural log of anything that's negative. The domain of natural log starts for all things that are positive x's and moves forward. So it's really important that when we integrate, we ensure that that x that we're going to take the natural log of is a positive quantity. Then, if we see that we have more complicated integrals, then you're going to take a look at U substitution. So it will review chapter 4. Okay, let's take a look. So I'm taking a look at the integral of 4 over x dx. If you remember, we are allowed, since that 4 is multiplied, I could rethink of this as 4 times 1 over x, which means I can think of this as 4 times the integral of 1 over x dx, because I can move constants in front if I'm multiplying. So that constant will just hang out in front. The integral of 1 over x dx is natural log of absolute value of x, and then I add my c because I don't have bounds. You might likely see them say that the answer is 4 natural log absolute value of x plus c. That's totally fine. But they may go back and say, hey, wait a second, since this is multiplied in front, I could send it back up and make it a power. So this is also equal to natural log of absolute value of x to the 4th, and then plus c. Or I could take a look and then really think about, hey, if I take something to the 4th power, it would be positive anyway. So I actually don't need those absolute values because the 4th power is going to ensure that I have a positive answer. So you are likely to see, if they move the 4 up, for them to just say it's natural log of x to the 4th plus c, and they're not going to include absolute values because x to the 4th is guaranteed to be positive anyway. So then looking at the second example, you may think it's silly as far as why it's there. You're going to, just like we did in example 1, move the 5 out, times the integral of 1 over x dx, so it's going to be 5 natural log absolute value of x plus c. That part is exactly the same and kind of a waste of time to repeat it. But I wanted to talk about if we go to move the exponent portion back up in this one, now you're going to be looking at natural log of x to the 5th And if you don't include those absolute values, you have a problem because x to the fifth is not guaranteed to always be positive. So how you would see this one, if they want to move the power back up, they're going to have to leave the absolute value bars around the x to ensure that it's positive, and then raise it to the fifth power. So I just wanted to draw your attention to what happens if you would end up with an even exponent versus if you would end up with an odd exponent. Make sure you think that one through. Okay, we've been through this for a few months now. You know your homework's not going to be that simple. So as we keep scrolling through, now let's do an example that's got a little more going on besides just x. So I see that I have 3x minus 2 in the bottom. And I know that if I could get it in the form 1 over u du, that I could integrate. It would turn into natural log absolute value of u plus c. So a good place to look for my u choice is the denominator. If I don't see any powers, and I don't see any radicals, the denominator is a good place to look for u sub. So u equals 3x minus 2. So du equals 3 dx. And then as I go back and I try to replace all my pieces, I have the integral of 1 over 3x minus 2 dx. I've gotten this bottom part replaced with u. Great. But I don't see this 3 that I'm seeing with my dx. I only see dx. So again, back to chapter 4 review, I'm going to turn this into 1/3 du is equal to dx. So now I can replace the dx with 1/3 du. And we did this quite a bit. We know it's easier if we put the 1/3 in front. 1/3 times the integral of 1 over u du. So 1/3 times natural log absolute value of u plus c. Okay. We're done with the calculus, but this original problem started with x's, so I need to make sure, since I don't have bounds, I didn't switch it over to any kind of u bounds, I need to make sure I go back and replace u. So I made a choice that u was going to equal 3x plus 2, so I'm going to replace the u with 3x plus 2. Oops, change colors. So this is going to turn into 1/3 times natural log absolute value of 3x plus 2, and then plus c. And then I would think through, do I need these absolute values or not? Well, yeah, I have no idea what x is. So if x is like -1, then this becomes -3 plus 2, and it's a negative overall that I'm trying to take the natural log of, which can't be. So I've got to leave those absolute values on. So that's my final answer. The only other thing they could do creatively with that is if they want to move the power, you would then need to think about, okay, the 1/3 power would turn into the cube root, but it is possible to get negatives with the cube root, so you would do natural log absolute value 3x plus 2, and you would think about taking the cube root of that. So natural log of the cube root of absolute value 3x plus 2, and then plus c. Because the 1/3 power is the exact same thing as the cube root. So if you're allowed to bring powers back up, instead of constants in front, you're allowed to bump them back up as powers, then you can think about fraction powers as radicals. But you do need to think through if it matters to make sure that the inside is positive. Well, yeah, because if I take the cube root of a negative, I'm going to get a negative back out. Actually, for any of your radicals, it matters that you put those in absolute values, because if you take the square root of a negative, then you're going to end up with imaginaries, and that's a problem as well. Okay. This next one, I want us to take a look at example, oh, no, I'm ahead of myself, never mind. Okay, looking at this next example. So, we've talked about that we think it's a good idea to let u be our denominator. So this just kind of looks like a mess overall. So let's start with it and see if it gets us anywhere. So if we let u be the denominator, then u equals x cubed plus 3x squared minus 4. So du equals 3x squared plus 6x, all of that, so in parentheses, is times dx. Okay. Well, I got the bottom part handled and replaced, okay, but now I don't see, so if I recopy my integral, I have this x times x plus 2 on top, and then I have the bottom, which I've replaced with u, but I don't see the top yet, and times dx. So now I need to go back and really look at this portion, because I got the bottom replaced with u. But I need to look at this top portion and see if that's what I have over here. Well, algebraically, I could take a look and say, okay, between the 3x squared and the 6x, I could factor out a 3x. So if I factor out a 3x, then I end up with x plus 2 dx, and I'm actually getting closer because I do see the x times x plus 2 dx. I see that over there. I just don't see the 3. And we saw plenty of times in chapter 4 how we can handle that constant in front. We could just divide it. So I could think about 1/3 du equals x times x plus 2 dx. And so now this top portion, yes, I can replace it if I replace it with 1/3 du. All right, so this integral is equal to 1/3 times the integral of 1 over u du. We took the 1/3 out and, oops, I don't want that. We took the 1/3 out in front, and then we now have the du part over here, and that left nothing else on top, so that's why it went to a 1 over u. All right, so then we integrate. So this equals 1/3 natural log absolute value of u plus c. And then our last step is just to go back. We have to replace that u. So if you go back and take a look up here, u is equal to that whole big denominator. So I turn this into 1/3 natural log absolute value of x cubed plus 3x squared minus 4, close your absolute values, and then plus c. Whoops, I don't want that. Plus c. Then the only other clever thing that they might choose to do is again rewrite that as a cube root. So natural log of the cube root of the absolute value of what we had. X cubed plus 3x squared minus 4. Then close the absolute value, close the cube root, and then do your plus c. They're less likely to turn those powers back into radicals when it's already like big and complicated like what we have. But a lot of times if it's just a plain x, they might move it back and look at it as an exponent. Okay. So it's these next couple examples that I wanted to take a look at. So 5, oops, I copied number 5 twice, miscounted. So 5 and 6, if we swap that out for 6. And then you'll have more room for 6 on the next page, but I want to approach the setup of 5 and 6 together. So far, what we've been doing is taking a look at our denominator for our choice of u. But in number 5, the denominator is pretty simple in comparison to the numerator. So I wanted to take a look at what if we let the numerator be our u sub choice. So if we do change colors. So if we do u equals 2x squared plus 7x minus 3, then du would be 4x plus 7, all of that, so in parentheses, times dx. Well, that's not what I have in the denominator at all. So that's not getting me to what I'm interested in at all. But I at least wanted to take a look. Then my other choice would be to say, okay, what if I take a look at u being x minus 2, because it is in the denominator. So then du equals dx, and then I'm kind of stuck. Then I would turn this problem into, I'd have the u on the bottom and the du to replace the dx. but then I would still have the 2x squared plus 7x minus 3. And we saw some ones like this last chapter. If you remember, if you come back up to this original and you're just a little more creative with it, and you turn it into u plus 2 equals x, you could then go replace all of these x's with u plus 2. But that's really ugly. Then you're going to have to FOIL out u plus 2 and distribute the 2. Then you're going to have to take 7 times the quantity u plus 2, clean all of that up, and then subtract 3. That's going to take you a while. So it's not that it's, again, you did your math wrong. Your math is fine, but it's going to take you a while. So we'll come back to this one here in a minute. Okay, let's come down here and look at 6. So again, same kind of deal. Our top is more complicated. So if we let our top be our u choice, so u equals x squared minus 2x plus 4, then du equals 2x minus 2, again, all of that, so in parentheses, times dx. I wanted to bring your attention to this because this looks promising, but it's algebraically not the same. I need you to look at the original problem and realize that we would need, to make the original problem work, we would need du equals 1 over 2x minus 2 times dx. These are not equal at all. So it looks promising by letting the u be the numerator because I'm seeing the du show up in the denominator. But I would need it to show up, I would need du to show up as a fraction. And the derivative of x squared something is never going to show up as a fraction. There are some times where a good choice is the numerator because the derivative of the numerator turns out to be a fraction. Then by all means try it. But if your numerator is working out and you're seeing its derivative in the bottom, but the derivative of the numerator is not a fraction, then that's a problem. Okay? So we're stuck here. So again, it's not that I did my math wrong, it's that this math isn't helpful. So the math isn't helpful on number 6, and we are kind of stuck. On number 5, we found a way around it from a method that we used last chapter, but it's going to be really time consuming and tedious, and so it's kind of less than ideal. So what I want to draw your attention to is that it's a good idea to try division first. When your exponent is bigger on top. Because you basically have an improper fraction. I'm also going to put in parentheses, in Calc BC, we'll see this a lot, when you have equal degrees on top and bottom. So we can kind of expand this technique throughout the year. But it's a good idea to try division when your exponent is bigger on top, when you have an improper fraction. So I'm literally going to think of this as a division problem. 2x squared plus 7x minus 3 in parentheses, divide by x minus 2 in parentheses. And then we've got to go review some algebra. So you actually have options here on this one to choose between synthetic division and long division. Because it's a plain x, there's no x squared, there's no coefficient in front of the x, it's just plain x. So if you remember synthetic division, we always switch the sign for the number in the box. And then we use our coefficients here from our first portion for what goes out to the side. So a 2, a 7, and a negative 3. So switch the sign for what you're dividing by for the number in the box. And then the rest, you copy the coefficients. And also, if you remember, you got to make sure these are in descending order by exponent, and that if you're missing a term, that you include a 0. Okay, bring down the 2. 2 times 2 is 4. So then we add for synthetic division, which is a change. So we get 11 22, negative 3 plus 22, we get 19. So we have turned this, that means that this original expression is equal to 2x plus 11, and then our remainder, so plus 19 over what we divided by, x minus 2. Okay, so that means our original integral, we have now rewritten to be the integral of 2x plus 11 plus 19 over x minus 2, close your parentheses, dx. Well, I don't need anything, any help as far as integrating the 2x, didn't change color again, the 2x plus 11. I don't need help there. But this 19 over x minus 2, I do. I need to do a u sub here. So if u equals x minus, oops, sorry. If u equals x minus 2, then du equals dx. And so I can change this into the integral of the 2x plus 11 in parentheses dx plus, change color, the 19 I could bring out as a coefficient, and then 1 over u du. I'm taking the time to rewrite this original, oops, that I moved around, this original integral, because I want to integrate all at one time so that then I can just do my 1 plus c and not have to worry about all the different c's. Okay, so I integrate the 2x, get 2 times x squared over 2, plus integrate the 11, get 11x, plus, I would do a plus c, but I'm just going to keep going and keep integrating. So plus 19 times natural log absolute value of u. Then I'm going to do my plus c. And then I'm out of room, so I'm going to move this other stuff here. Yeah, let's move down there. All right. So then to clean up, I can see that the 2's cancel. That's really nice. And then I just have my last step of replacing this u. Okay, so final answer is going to be x squared plus 11x plus 19 natural log of absolute value, and go back and look at what u was. U was x minus 2. And then close your absolute values, and then plus c. So that's my final answer. They could come back and take this 19 and make it an exponent, and then you'd have to think through, if I raise something to the 19th power, is it already positive or not? No, not necessarily. So I would need to keep my absolute values. But with the 19 being so large, it's probably going to be rare for us to want to work with something to the 19th power. So you're probably just going to see them leave it. Okay. So then, like I said, we talked through setup on 5 and 6. If you're going to let the u be the numerator, the only way that really works to your advantage then is if when you differentiate you're getting a fraction. So it didn't really help us on 6. And like I said, you guys have more space on the next page. I just kind of wanted the setup of both of them on the same page. All right, so if you notice on number 6 though, the exponent is bigger on top. So we're going to take and try division. But if you notice when we go to divide x squared minus 2x plus 4, divide by quantity 2x minus 2, this is now a problem. I have a coefficient in front of my x, so I cannot do synthetic division. So you have to remember back from algebra, Algebra 2 and math analysis, you are not allowed to do synthetic division if you're dividing by something that's an x squared and x cubed where there's an exponent, or if there's a coefficient in front. So now we got to review long division. So 2x minus 2 is out to the side. And then inside your division part, you have x squared minus 2x plus 4. Then to figure out this first component of what goes up on top, you need to think about what is x squared divided by 2x. So that would be 1/2 x. So I'm going to put a 1/2 x right there. Then I'm going to multiply by what's out to the side. So that would turn into 1x squared minus 1x as I distribute and multiply. Then if you remember on long division, we always subtract, but you need parentheses there. We subtract all the way through. So x squared minus x squared, that cancels. If that first term does not cancel when you do your subtraction, you did your algebra wrong. You put the wrong term up on top, and you need to go check it. Now, be really careful. So some students like to come back through and change this to a plus, this to a minus, and this to a plus, so that they make sure that they were going to subtract everything. So it's really negative 2x plus x, so negative x, and then we bring down whatever's left. So we bring down, change colors, plus 4. Okay, now I need to take and figure out what is negative x that I see down here divided by 2x. That's going to be negative 1/2. So I put negative 1/2 up on top, and then I distribute over here and multiply. So that would turn into negative 1x, and then that would turn into positive 1. And again, remember I'm subtracting this entire thing. So a negative x minus a negative x, those cancel because you could distribute and make this a plus, and then this a minus. So then 4 minus 1 is 3. And I'm done now because the degree on the 3 is smaller than the degree up here on the x. Or another way of thinking about it is your next piece would be to take 3 over 2x, and you can't clean that up. You end up with a fraction, and that's actually how we get our remainder idea. We're going to take 3 over 2x minus 2. But whenever this degree-wise is smaller than what you were dividing by degree-wise, you know you're done. So then the answer to the division would be to add 3 over what we divided by, 2x minus 2. Okay? All right, so I have turned my original problem into the integral of 1/2 x minus 1/2, then plus 3 over 2x minus 2 dx. And I actually need a u sub here. I can integrate these other pieces just fine, but on this last piece I need to let u be 2x minus 2. So du equals 2 dx. But I don't see a 2 dx, I see a 3 dx. So I need to be clever there and go ahead and divide. Think about 1/2 du equals dx. Okay, so now I can turn this into, never mind, sorry, the integral of 1/2 x minus 1/2, all of that dx, plus, I'm going to bring the 3 out in front. Then I'm going to think of the 1/2 that I want to have with my du. Then I'm going to think of integrating 1 over u du. So this 1/2 du was coming from that dx. And the 3 was just a constant, and so I moved it out in front as well. Okay, so then I get 1/2, the x goes to x squared over 2 minus 1/2 x. I would have a plus c, but I'm not done integrating yet. So plus 3/2 natural log absolute value of u. Now I'll do my plus c. And my last step is just to go back and replace this u with 2x minus 2. So I get 1/4 x squared plus 1/2 x. Oops, sorry, I miscopied. Minus 1/2 x. and then plus 3/2 natural log absolute value of 2x minus 2, close absolute value, plus c. This is one of those, you guys never like it, but this is one that they can do some other algebra with because the 2x minus 2 is factorable, and then there's a lot of things they can do with this natural log with algebra properties and log properties, lumping things in together with the plus c. I'm not going to go over that right now. That'll be a good thing we can talk about as like a second repetition kind of thing. Okay, algebra reminders. You need to make sure that you understand algebra really well in this chapter, and that if you're struggling, you come in and get some help. So division helps us rewrite, and we've got that quotient portion and then the remainder over what we divide by. Oftentimes that remainder over what we divide by is where we're going to take a look at u sub, because usually the other portion is okay to integrate. You can only use synthetic division if you have a number plus, or sorry, an x plus or minus a number. If you change that up and that x has a power or that x has a coefficient, then you have to use long division. And we reviewed both. Okay. So we've reviewed the hard algebra. Then a lot of you struggle with trig too, and that would be the last piece of this. You already know these from chapter 4. You are responsible for already knowing how to integrate all of these. Then in chapter 4, we showed you that there are some other trig functions that it's possible to integrate, but we said at that point you didn't have to have them memorized. Now you do. I'm going to show you how to prove the top two. The bottom two, it's really better for you to just memorize them. The top two, you can get away with doing u sub and make them work. So I'll show you that. Okay. So let's start with cotangent, for example. So say that you haven't made flashcards or memorized and you're just stuck and you see that you're supposed to integrate cotangent. Rewrite cotangent as sines and cosines. So this is now the integral of cosine of x over sine of x dx. And after what we talked about today with division, it's a good choice to let our u be the denominator. So u equals sine of x. So du, derivative of sine, is cosine of x dx. Looky there, that's what we have. So I've turned this into the integral of 1 over u du, which means my answer is natural log of absolute value of u plus c. And then it's just my job to get rid of that u by replacing it with sine of x. So I get natural log of absolute value of sine of x plus c. And if you look back up, that's what they tell you that you're supposed to memorize. So we proved it with u sub. I guess maybe I shouldn't have the check. You're not checking, but we proved it with u sub. So we can also get that with u sub. Well, same here. If you want to change tangent into sine and cosine and then let your denominator be your u, you can easily make this work out with u sub as well. The bottom two, you have to be really clever with what you're going to multiply by to make them work out, and it's just really not worth your time, so you need to memorize the bottom two. The integral of secant is natural log absolute value of secant x plus tangent x, not multiplied, added. And then cosecant just has a negative in front, natural log absolute value cosecant x plus cotangent x. Okay, last one. So we now need to integrate from 0 to pi over 4. So this is our first time seeing bounds again, and it'll review how we do u sub with bounds, so that's good. But as we take a look, there is nothing on these lists of trig functions that helps me integrate the radical of secant squared x minus 1. So I need to be a little more creative and think about this in a different way, and hopefully you're automatically thinking of those Pythagorean trig identities. So sine squared of x plus cosine squared of x equals 1. If I want to end up with secant, I would then go through and divide everything by cosine of x. And so sine squared over cosine squared would give me tangent squared of x. Cosine squared over cosine squared would give me 1. And 1 over cosine squared would give me secant squared of x. So I'm going to use this identity, which I got from dividing by cosine squared of x all the way through. And then I'm going to rearrange and say, okay, so that means tangent squared of x equals secant squared of x minus 1, which is what I happen to have over here inside my radical. So I can turn this into the integral from 0 to pi over 4 of the square root of tangent squared of x. Well, that's really convenient because when I square root a square, they undo each other. The only problem is, you may or may not remember this from algebra, the square root of x squared is technically absolute value of x. The fourth root of x to the fourth is absolute value of x. Because numerically with these even powers, if I want to square root -3 quantity squared, and I just say that's -3, think about that. That doesn't make any sense. That's really the square root of 9, and the square root of 9 is 3. Well, how do you make those two the same? Well, you make those two the same by putting the -3 in absolute values. So when a square and a square root cancel, yes, they cancel, but you need absolute values. So this turns into absolute value of tangent of x. And we've reviewed how you integrate absolute value of something. So now I need to think through where I'm at to know if tangent of x is positive or negative. So with my bounds going from 0 to pi over 4, that's in quadrant 1. In quadrant 1, tangent of x is already positive always. But if not, if you switch quadrants and you switch values where tangent goes from positive to negative, then you would have to go back from chapter 4a when we talked about like distance and displacement. And we talked about how you split up and integrate with absolute values. That's a skill you're still responsible for. I just don't have to worry about it here. It turns out this is really just equal to the integral from 0 to pi over 4 of tangent of x dx. Now, you can pause this and choose to do u sub because you don't want to memorize the trig rule, and in which case that's a good practice for you of how to change your bounds over and how u sub works. Or you can say, nope, I'm going to memorize. I'm going to make flashcards, whatever it takes. I'm going to memorize all these trig rules. So I'm just going to look at this and look from above, from my above rules, and say, hey, I can integrate tangent and get negative natural log absolute value of cosine of x. For me, I usually do u sub on tangent and cotangent. It's just one less thing to remember. But if you want to memorize them, you can memorize them and go straight here. In which case I stayed with x all the time so I don't change my bounds. If you do u sub, you do change your bounds. So again, the nice part about it being a video, pause and do your own thing. Do whichever way you think you would do. Then we should all get the same final answer. So if I plug in, I get negative natural log cosine of pi over 4 is root 2 over 2, and absolute values really aren't going to matter there, minus a negative natural log, so that's really plus, of absolute value cosine of 0 is 1. And so then I could leave it. I need to go back and clean up a little bit. If you remember when we looked at the natural log graph, every log graph goes through the coordinate 1, 0. Natural log of 1 is 0. You're expected to know that. Don't leave an answer with natural log of 1. But I could leave an answer negative natural log square root of 2 over 2. You're just not likely to see that. How you are likely to see it, they can clean this up and say it's 1/2 natural log of 2 with algebra rules. Algebra rules, exponent rules, log rules. So work on that and To see what you're able to do, I would pause this and try it on your own. What you can do to get from there to there is think about this as negative natural log 2 to the half over 2 to the first. So then exponent rules tell you to subtract exponents but keep the bases the same. So that'd be 2 to the minus half. And then I could move the exponent in front, and I already have a negative times another negative. I could get there. There are tons of ways you can do this. You could also go back and say, hey, this is division. I'm going to split it apart. There are lots and lots of algebraic ways that you can make this work, but you are more likely to see a cleaned up answer. It is okay if your free response to leave this. It is not okay to leave natural log of 1. Make sure you know that natural log of 1 is 0 because every log graph goes through the point 1, 0. Okay, that finishes up 5.2.